Hey everyone, in this video, let's take a look at question 322, coin change on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question, you're given an array coins representing coins of different denominations and an integer amount representing the total amount of money. We want to return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any number of combinations, then we want to return -1. We can assume we have an infinite number of each type of coin. Let's take a look at the example here to see what we're dealing with. But in this first coins over here, we have the coin 1, 2, and 5. So you can think of this as like a $1, $2 bill, and a $5 bill. And then we want to return $11. So how can we do this? Well, there's many ways, right? We can do maybe just a bunch of $1 bills. We can do maybe 2, 4, 6, 8, 10, and something like this. But it turns out that this is the fewest amount of coins we can use, 5, 5, and 1. In the case for something like this, we actually can't form it. We actually can't form the number 3. So return -1. And here, if like amount is 0, then automatically we can't form anything. So maybe we can start off with that. So if amount is 0, just return -1, right? Or I guess just return 0 because there's no way in which we can form like 0 coins. Okay, so this question kind of looks similar to something we've done in the past, right? The combination sum question. So in combination sum, what did we do? Well, we had an array and we basically returned all of the list of the combinations that added up to a target. And so this question is actually pretty similar, right? Because you can think of this as like all of the list of combinations. And all we're really doing is we're just returning the length of the smallest one. So maybe let's go ahead and start off with that. And I already have a video about this, so I'll try to go through this pretty quickly, but let's maybe see if we can start off at that and then work our way to a better solution here. Okay, so what did we do in the combination sum video? When the combination sum went, we essentially had a result variable, and this result variable kept track of all of the combinations that we could form. And then what did we do? Well, then we had our helper call, which basically tried to form all of the list of combinations. And then in the end, we just went ahead and returned our combinations. Now here, we don't actually want to return the combinations, right? Here we want to return, what do we want to return? We want to return the list of the smallest combination. For example, res over here might be something like this, and then 2, 1, I need one more, and then 5, 5, 1. And basically we want to return 3 over here because this corresponds to just 3 elements, the fewest elements. So what can I do? Well, firstly, I can just check, right? I can check if result doesn't exist, then I couldn't form any combinations, right? So I'll return -1 here. Otherwise, I can go ahead and sort result, and I will sort it based off of, so I'll do lambda x, I'll sort it based off of the length of x. Basically what this means is that this value here will come to the start because it has the shortest length. And then I will just return the length of the first element. Okay, so now we have our driver function. Let's see how we go about doing our helper call. And again, I'm going to go through this relatively quickly, but if you want some more detailed explanation, go ahead and watch the combination sum video where we calculated all of these combinations. But basically, what do we do? Well, this is a backtracking type question, right? What we do here is like we try to consider 1 and we consider it again and again. And at the start, we'll consider all 11 ones, and then we'll try to consider a 12th one, but that's out of bounds, right? So then we backtrack and then we try to consider a 2, but that's also going to be out of bounds. So we backtrack again, and then we basically like form all the list of combinations in that sense. So kind of in a backtracking type problem, what we always do is we have the same sort of helper function or like the same sort of definition. So what do I need to pass in? Well, I need to pass in the list of coins. I need to pass in like res over here, which is my master list. I need to pass in cur, which will be like the sub list that I'm forming that I eventually add to the master list. I need to pass in amount because I want to know like how much I still need to like create. And then I need to pass an index so I know like where I am in the list. Because for example, after I consider all of these ones, then I do a recursive call and then I again need to start off at the 1, right? So that's just part of how we do these. Okay, so what is our base case here? Well, if you think about it, let's assume amount starts off at 11 and we use a coin, right? Maybe we use coin 2. Well, if we use coin 2, then now I need to form 9. I need to form $9. So if you think about it, our amount, if it's equal to 0, then I know I'm at my solution, right? So what I can do is I could append to cur, I could append to res a copy of cur, and then I go ahead and return. This is how we append. And now what do we do? Well, now, if this is not the case, I want to look through my list of coins. Okay, so how can we do that? Well, I can do for I in range. I will start from index, and I will go to the length of coins, which in this case is just coins here. Okay, now I'm starting off at index again, actually in this question, even when we do a recursive call, we'll still actually just go back to the front. So we don't really need to start off. We don't really need to pass in index here, but this is how I like to do my questions because the format stays the same. Okay, so now if we want to consider coin I, how can we even know whether we're valid or not, right? Well, coin I, it has to be less than amount, right? Less than or equal to amount. So we can do something like if amount minus coins at I, if this is greater than or equal to 0, then we can consider this coin. Otherwise we can't, right? Because it's as if like amount is equal to 2 and we're considering the coin 5. Well, this doesn't work, right? So we want it to be greater or equal to 0. Okay, so if it is this case, then we can consider this coin, right? We can add it to our combination. So we'll do cur.append coins at I, then I do my recursive call, and then I go ahead and pop it at the very end. And this is always how we do our backtracking type question. So take a look at the combination sum question if you want some more detail on this one. But essentially, we go ahead and we add in all of the ones, and then once we reach, like, once we are out of bounds, basically, or once we add in more than, well, I guess we won't add in more than we need, but basically when we return from the one call, we'll have 10 ones, right? And so then, because we popped the 11th one, so then we'll have 10 ones, and then we'll try to add in the 2. Well, we can't add in the 2, so try to add in the 5. We can't do that either. So then again, we'll go back, and then now we'll have 9 ones because we go ahead and pop. And then we'll try to add in the 2. And so then we can form a combination in that sense. Anyways, that's just like the highlight of how we do these questions. So what do I have in the helper call? Well, coin res cur amount has to be amount minus coins at I, right? Because we want to find a lower amount now, and the index remains at 0. And so that's pretty much all there is. So let's go ahead and do coins res cur, which is an empty list. Amount remains the same. Index, we start off at 0. So let's go ahead and run this to see if we arrive at the solution. And we do. So let's go ahead and submit. So obviously we're doing much more work here than needed, but I think it's like a good starting point because it allows us to transition our problem into a better one. Okay, so we get memory limit exceeded. So if you think about like why that's happening, right? Like we're creating a lot of memory limit. Basically means either you're doing too many recursive calls or your your set or your list is becoming too large. So if you really think about this, like we don't really need to form like cur, right? Because we're not interested in the combinations themselves. We're just interested in the smallest amount of coins used. If you think about this, we can actually improve this. What can we do? Well, maybe we can do something like we just record like the amount of coins that we've actually used. So maybe here I can do something like coins used, right? Coins used, something like this. Coins used. And so I can actually go ahead and remove cur. So let me go ahead and remove cur. It'll clean this function up quite a bit. So I'll remove cur here. I'll remove cur here. I'll remove cur here. I'll remove it here. Now what do we need to do? Well, now coins used, we need to increment this by 1. So actually here, we need to say we've used 0 coins at the start. And now if amount is 0, then I just want to return coins used. Okay, so we're almost at our solution. Now, what can I do at the start, right? So if you think about it, I actually don't need res here at all. So I will also remove res. Let me go ahead and remove res from this. Okay, so if my amount is 0, then I'll just go ahead and return the coins used, right? So now, when I'm returning from this helper, I basically figure out how many coins I've used in this recursive call here. But I need to like basically map that to a minimum, right? Through all of the recursive calls, I want to know what is the minimum. So maybe I can do something like answer, and we can set this to like a big value, like a infinity. And then what I could do here is I could do something like maybe this is like my I don't know, like let's just call it I don't want to call it coins used. Let's just say CU, for example, right? For coins used. And then what I could do is I could do answer is equal to minimum of CU and what and answer, right? So that's going to be my answer. Okay, so now we have answer is equal to minimum of answer, which is infinity, and then this thing here, and then we can just return answer at the very end, which basically means that I don't actually need to do this res is equal to sorted or anything like that. What I can actually just do is here, I can have my result, and then I can check if result is equal to infinity, then I know I couldn't form a combination, right? So in this case, I'll return -1. Otherwise, I can just return result. And so this is another way in which we accomplished the same problem, but we limited the amount of like stuff we needed to do. So now let me go ahead and submit to see where we're at. So this time, hopefully we don't get a memory limit, but we might get a time limit exceeded, which is fine, but at least we're going in the right direction here. So let's go ahead and run this. We get a time limit. Okay, perfect. So we know how to fix that, right? Whenever we're doing a recursive call, we can memoize our solutions to basically make it go faster. So how can I do that? Well, I need to pass in a dictionary here, and these two will be my memo. Now, what do I need to store in the memo? Well, I need to store whatever is changing, right? And if you notice here, there's two things that are changing, right? The amount and the coins used. So what I could do here is I could do memo at amount and coins used. This is equal to my answer, and I just return that answer in the very end. And then in my memoization call, I can just check if amount coin used is in memo, then I just return memo at this information here. So now if we go ahead and run our test cases, it runs. Let's go ahead and submit. We can see here that it's actually a different answer. So if we go in details, I think we passed in most test cases, but okay, we didn't. So we still have to make this a little bit better. Okay, so how can we make this better? So we used memoization. We used recursion, but it still did not allow us to come to our solution. So what's a further way in which we could optimize this? Well, we would have to use dynamic programming. So let's take a look at how we can use dynamic programming to arrive at the solution. So now let's talk about a dynamic programming solution, which is going to be our best solution here. So how can we go about doing that? Well, in dynamic programming, if we already have the memoization solution, then we can very easily come up with the DP type solution. Because all DP is doing is it's performing memoization, but without the recursion. Okay, so how can we do that? Well, in dynamic programming, we need a dynamic programming array, which will basically store our solutions in the midterm. And what do I need to store in this dynamic programming array? And also, what should the size of the array be? Well, we get that information over here, right? If you take a look at the memo, we're caching the amount and the coins used. So you might assume that our DP should be like 2D array here. But if you really think about this, the only thing that the DP really needs to cache is this thing here, this amount minus coins at I, right? Because this over here is like our solution. This over here is our solution. So this is actually not really part of the dynamic programming array, like the overlapping subproblems. The only thing part of the overlapping subproblems is anything that's to do with the actual array, to do with the actual coins, which is just this information over here. This thing over here is just part of our solution, which we will calculate when we're doing the solution. But this is not something that should be stored in the dynamic programming array. So dynamic programming, if you think about it in terms of like the variables passed in, like if you passed in two strings, then often it's going to be 2D. If you just passed in one array, then often it's just going to be 1D. And here you can actually just see that the only thing that changes with respect to the array is this one item over here. So that's why our dynamic programming would just be a single dimension. Okay, so what should the size of the dynamic programming array be? If you think about this, what do we have? Well, we know that amount at the maximum, it can be just amount, right? So maybe our dynamic programming, it can be of size amount, and then notice how it will go all the way to size 0. So what can we do? Well, let's just go ahead and figure out what we want here. So we can do like something like amount plus 1. What do I want to put in here? Well, what would this be encoding? This will be encoding all of the like the minimum amount of ways in which I can form a specific amount. So this DP array will encode the minimum way I can form amount 0, amount 1, 2, all the way to 11. So if you think about this, like because I'm taking the minimum, it wouldn't make sense to put 0 here because then this value here would never change. So maybe we can start off this as like a big number, right? Let's just start it off at like float infinity. So there's like in order for us to form the value 0, we need an infinite number of coins. Same thing for value 3, we need an infinite number of coins. And so then, like, when we're actually doing our dynamic programming solution, we will decrease it to the actual value we want it to be. Okay, so that's all good. Now, why do I have amount plus 1 here? It's simply because of, like, so I can easily, like, refer to the index. That's pretty much it. And also because, like, I will have a, like, so in the end, I can just do, like, dp amount, right, to return my solution. Also, like, I might, if we do something like this, we might arrive at like the value 0 here. So it would be very convenient to have dp at 0 actually refer to like 0 amount, and dp at 11 actually refer to as 11 amount and not like the amount of 10. So that's just the reason I'm doing this here. Okay, so we have this. Now what do we need to do? Well, we have to fill in our base condition, right? So we actually have our base condition here. If amount is 0, then the output should be 0. So in that case, if dp of 0 is given, then we form 0. So basically, the minimum way in which I can form amount 0 is just 0, right? I don't need any coins. I don't need any, so minimum coins I can form. Okay, so we have this. Now what do we need to do? Now we just go ahead and copy what we have over here. Now, notice that here, this amount, right? This amount is actually passed in, but here our amount is in a list. So basically, I need to perform this thing for every single one of the amounts, for amount 0, for amount 1, 2, 3, 4, all the way to 11. So I can go ahead and do this. So I can just do something like for amount in range, and I'll actually start off at amount 1 because we already considered amount 0 here. Amount in range, 1 to length of dp, and now I can basically just go ahead and follow this. So I can do for I in range, and I here will be my coins, right? And you can see index always starts off as 0, so I would do 0 to length of coins. And then what will I check? Well, we'll just check what's exactly given here. So I will check if amount minus coins at I, if this is greater than or equal to 0, well then I can go ahead and consider this coin. So how do we go about doing this? Well, remember that in dynamic programming, our helper call here will be replaced by the dp call. So maybe I can do something like cu is equal to dp of what? Well, it would be equal to dp of this information that I'm given here. Now, what am I given here? So if you think about this, here we're decreasing the amount of coins used, right? Because we're actually taking a coin into consideration. So I can do amount minus coins at I. But notice that this will just return to me the minimum coins I need to form this amount. So if we had maybe like the amount 10 and this coin over here is like the coin 3, this will return to me the minimum amount of coins I need to form 7. So if we have that, we still need to add on like the current coin, right? So that's what we have over here, coins used plus 1. So then I will add in plus 1 here. Otherwise, if we already calculate this one, I still need to calculate my overall answer, right? So my overall answer is just this. Now, what is my answer? My answer is just what's in dynamic programming of amount. So I can do dp at amount is equal to minimum of essentially the cu here and dp at amount. And so this is my solution in dynamic programming. Now, what do I return at the end? Well, I can return essentially dp at amount, but we need to be careful that this is not infinity, right? Because if this is infinity, then we return -1. So we can actually just check. So we can check if dp at amount is equal to float infinity, then we just return -1. Otherwise, we return dp at amount. And that's basically it. So let's go ahead and run our test cases here to see if we arrive at the solution. So we do, let's go ahead and submit it. And perfect, we arrive at the solution. So this is actually the best solution, even though it's a little bit slower here, but it is still the best solution here. So this is how we went from a recursive approach all the way to a dynamic programming approach. What is the time here? Well, it would just be like the amount times the number of coins. So it looks like that is the time complexity, and the space complexity is just the total amount, as we're just storing that in the dp array. Okay, thanks for watching.